think he was applying to. Yeah, it's a non-commuting inverse system.
I think so. I only just plugged it in. So.
What made you think of that?
Well, this is way after.
I keep at my apartment. Shared friends. Co-heat.
Did you turn this on? So apparently you voted on.
Time to start now.
5 minutes ago.
Oh. Okay. Accidental late start. Before I move on to mixed states, let me actually make 2 comments on the time evolution for spectral functions. So one, I should say, this real-time approach I was talking about is definitely not the only way to do it. There's also a way to work directly in energy space. So the idea is, suppose you have some spectral function S of E. There's a technique called Chebyshev expansions, where you replace this with some alpha n, where these are a series of orthogonal polynomials called the Chebyshev polynomials. And then the goal becomes to compute alpha n. And if you can keep enough terms in this expansion, you can get an accurate spectral function. And so the basic technique you can show is to calculate the alpha n's. I'm going to be very schematic because I haven't prepared notes on this. You need to do something like calculate the ground state, act with the operator of interest, and then compute let's see. It depends on the spectral function exactly. But roughly speaking, you need to calculate matrix elements between 2 states and some power of the Hamiltonian. So in this approach, what you do is you prepare the ground state, flip a spin, and then act with powers of h and compress it, evaluate these matrix elements in this algorithm to compute from that these Chebyshev moments, and then from that step you get S of E. I don't know actually of a study which compares which is more efficient. One of them makes better movies though, which is to do the real-time case. The other thing I want to talk about is why are the spectral functions not so difficult to get? So let me contrast 2 types of time dynamics we could do on a pure state. So one of them is the global quench, where suppose I have a Hamiltonian H, and at time t equals 0, I start with a configuration like all up, which is not an eigenstate with respect to that Hamiltonian. So if I was to compute the ground state energy H, sorry, not the ground state energy, the average energy in this, it would be the ground state energy, which we'll call E naught, plus some constant that scales linearly in the system size, right? So there would actually be an energy per unit length. Okay, so if I now time evolve e to the negative I th on this initial state here, t, what's happening here? Well, I have a pure quantum state time evolving, and this state has finite energy density, so I expect that at long times, this is going to look like some thermal state, so I'll write that as ETH. Just if you assume there's eigenstate thermalization or the system's ergodic, at long times you'll get a pure state, but if you look at any local observable, it will look like a thermal state. So in particular, let's figure out what that means about the entanglement at long times in this pure state. Well, if I look at the system and cut out a region A and the complement B, what ergodicity means is that if I look at the reduced density matrix in region A at large times, this is actually beginning to look like a thermal density matrix, e to the negative beta HA over Z, at some temperature here, which is set by the energy density in the state you start the quench from. So in particular, we can ask, what is the entanglement entropy in this region here, SA? Well, it's negative trace rho A log rho A. And if at large times the local density matrix looks like a thermal one, then this entropy is just really the entropy we talk about in StatMech. Not entanglement entropy, it's just the thermal entropy. And thermal entropy is generally extensive. So it's going to go like some constant S times the length of region A. Okay, so this is in stark contrast to the area law, where the entropy of a region only goes with a boundary, which in 1D would just be a constant. Now the entropy goes like the entire length of the system. That's the volume law. And the way that manifests in the time dependence is that if I instead do the cut into the left and right and measure the entanglement just in the left versus time, I mentioned this earlier, you'll find it goes up, keeps going up linearly. Okay, so when you do these global quenches at finite energy density, entanglement goes up linearly, so the cost to do pure state matrix product state calculation blows up exponentially. So what's different about calculating these spectral functions is you don't do a global quench. What you're doing is you start with a ground state, and then you act with just a single spin flip, say, on site 0, and this is the thing you time evolve. And if you ask, what is the energy of this state? Well, you only flip one spin. So rather than having an extensive amount of energy, there's only order 1 energy, which means the energy per unit length is actually 0. So in other words, this state, even though it's an excited state, is still at 0 temperature. So when you go to long times, you don't actually expect it to evolve towards a volume loss state. Instead, if I look, for instance, at the entropy on the left of a cut, it starts at the value of the ground state, and then something kind of complicated happens, and then it will just saturate. Basically, what's happening is you introduce a particle, and the particle sometimes flies to the right, sometimes flies to the left. That uncertainty contributes this change in entanglement, but then it doesn't introduce additional entanglement beyond that. So that's why you can tend to do the time evolution out to long times without encountering the barrier. Yeah?
Is quench initiated by flip-up spin, or is there time-dependent term in Hamiltonian?
Well, to calculate equilibrium spectral functions, this ground state is an eigenstate of H. H is time independent. And the dynamics is introduced by the fact that you start out by flipping a spin and then watch it propagate. Yeah. Okay, so in the next part of the talk, I actually want to discuss, suppose rather than computing equilibrium spectral functions, you do want to model behavior like this. So thermalization, you start in something which is not an eigenstate or not an equilibrium state, and then you time evolve and want to see what quantities like the energy density or magnetization do. So that's what I'm going to talk about, time evolution for mixed states, and a particular method I've been thinking about. So I should say, people are, okay, so dynamics for non-equilibrium 1D states, there's a whole ton of different algorithms people have come up with and are still developing it. So there's METS, which is minimally entangled typical thermal states, the time-dependent variational principle. You can use purifications. So the method I'm going to tell you about is certainly not the only one. But here's the approach I'm going to discuss. So suppose I want to follow the time evolution, not of a pure state, which is what the matrix product state was, but actually of a density matrix, so a mixed state. Okay, so the first thing we need to do is decide how are we going to store, compress the information. Well, it's not too hard. We can also write down a matrix product type ansatz. It's just that now, because I need an operator rather than a state, on each site there's two legs coming out corresponding to bra and ket. It's an operator rather than one leg coming out as it was for an MPS. So this is called a matrix product operator. Now, one useful thing to know, there's actually a proof of this for field theories, is that if you have an equilibrium state, so if rho is a Gibbs matrix, e to the negative beta h, then there's always an efficient MPO representation of the Gibbs state, and the size of the tensors you have to use, the bond dimension, is at worst a polynomial in 1 over temperature. That worst case scenario is what happens for gapless states, conformal field theories. Then it diverges as the infinite temperature with some polynomial set by the, with some power set by the central charge. Okay, so this should work well if we're in equilibrium. Now, suppose you want to do some sort of time dependence. We can use the same trotterized approach as before. So the only difference in time dependence is you're now conjugating by the unitary evolution. Each unitary evolution before, you can split into the odd and even gates. And now it's just acting from two sides rather than one side. But if you just fold this thing over, the picture is exactly the same as the MPS. So the most naive approach you could do is say, rather than thinking of this as an operator, I'm just going to pretend these two legs correspond to the wave function of, say, a two-leg ladder. So you can always view an operator as a state by viewing the bra as a ket. And then we happen to be evolving under a special Hamiltonian which acts independently on the two sides, but formally now it's just the same as time evolving a pure state. And then you do the TBD algorithm. So I mean, this method goes back to soon after TBD, so for instance by Swallow and Vidal. And the way to summarize that is just you view the MPO as an MPS with twice the Hilbert space. Yeah.
But should be Hilbert space squared or 2 times?
It's the tensor product of the two Hilbert spaces, so the dimension of it is squared.
Yeah.
It's squared per site. Yeah. But here's the problem with this approach. I mean, that approach I think will work pretty well if everything is near local equilibrium. But here's why it's not going to work in this quench situation. So suppose our mixed state rho of T, or our density matrix rho, is actually a pure state, so it comes exactly from this quench scenario. And imagine the dynamics are thermalizing. Okay, so what thermalization means is that if you look at the behavior of this density matrix at long times, and you trace out the rest of the system and only look at a local density matrix, so I'm going to trace out the rest of the system and look at, this is a reduced density matrix on a region A, then at large times the local reduced density matrices look exactly like the reduced density matrices of a thermal state. I mean, that's what the ergodicity means, so local equilibrium. Now, we know from that result of Barthel, actually, that this is guaranteed to have an efficient MPO representation, and that holds true if you trace out and look at a local one as well. So what we know is that this particular density matrix locally has an efficient MPO representation. But the problem is, if you look at the entire density matrix, it's actually going to be having extremely large bond dimension. That's because that density matrix, okay, let me write out here. How would I write that density matrix as an MPO? Well, it's just two copies of the underlying pure state. It's like the density matrix rho, which formally is some ansatz like this. And this special case I'm considering here is actually just two copies of the MPS representing the pure state, right? So the bond dimension I need to use for this MPO here is just the product of the bond dimensions for the MPS, for the pure state. But according to that argument over there, the pure state actually has volume law entanglement. So the bond dimension chi is going like some exponential in time, right? So the density matrix you're trying to simulate globally has an exponential blow up in the bond dimension, even though any local, like if we were to look at the reduced density matrices, all of those should eventually look simple. There's some sort of contradiction here that this is actually should be, if you only want to know about local properties, everything's simple. But by storing the global density matrix, it looks exponentially complicated. So one way to formalize that is to say that at very long times, this perverse density matrix differs from the thermal one. Locally, they look identical. They look thermal. They only differ because the guy on the left contains some very large, many body operators, extremely complicated, that you never be able to measure. And that's what's contributing to this exponential blow up of entanglement. It's those very complicated operators encode the fact that it's secretly a pure state, even though they're not measurable. So suppose what we wanted to do was study the behavior of local observables. You know, you want to know about hydrodynamics, diffusion, energy transport. We don't really care about keeping track of these really complicated many-body operators inside the density matrix. Well, it depends what you want to study, unless you're trying to like very quantitatively look at chaos and scrambling, which is actually about the rate at which these are being generated. But if you're interested in hydrodynamics, you don't really care about them. But the problem with TBD is, you know, TBD uses this singular value decomposition to compress a state back to a matrix product state. And if you ask, what is it trying to optimize when it does that? It optimizes the overlap. It tries to make the overlap as large as possible. And in the operator language, what that means is that you're doing the MPO truncation in order to minimize the Frobenius norm, which is just that you just treat rho as an operator, or you treat rho as a state, and you look at this distance, and then it's minimizing this. But the problem with minimizing a distance like this is it treats all operators, whether or not they're local or very complicated and global. It gives equal importance to them. So the TBD is trying just as hard to keep track of the big complicated operators as the simple ones. But what you can imagine is when I define the minimization, I could actually choose any type of metric I want. I don't have to use this Frobenius norm. I can imagine trying to cook up a different way of weighting the operators where I say that local operators are big and complicated operators are small. And then what I'll be trying to do is using my sort of entanglement budget to only keep track of the local operators. So what I'm going to tell you about is like one guess for how to do this, but I would say in general this is more like an open research problem. What is the best way when doing these matrix product operator dynamics to compress them and truncate them? So maybe some of you guys will have ideas for a better way than what I'll talk about here. So Chris White at Caltech is the one who did most of the work here, and part of the inspiration for our approach is something called the BBGKY hierarchy. So here's how the BBGKY hierarchy works. Imagine you have a Hamiltonian which is local, so maybe it only affects m sites at a time. Then it's pretty easy to show that if you want to keep track of the time evolution of an n-site density matrix, you only actually need to know the density matrix which has m minus 1 more sites. So for instance, let's do this for one site density matrix. So this is a particular density matrix, reduced density matrix just for site j. Of course, the time dynamics is just the Heisenberg equation here, tracing out, so this is the total density matrix, do the Heisenberg equation and trace out the spins you don't care about. If H is a sum of two local terms, you'll find that there's only actually two terms that contribute, and you only actually need to know the two-site density matrices, the two-site density matrices which include the spin of interest. Okay, and it would be similar for the two-site density matrix. For the two-site density matrix, you need to know the 3 you know to the 4. And this is called the BBGKY hierarchy. There's also a version of this in classical mechanics. Okay, but so far this doesn't help because in principle, you need to know all the n-site density matrices. But what you do in the BBGKY hierarchy is you decide, okay, once I get to some complicated like n-body operator, what you do is so you have a term you need technically on the right, which is an n-body operator. But what you do is you approximate it by replacing that density matrix with its disconnected component. So you guys might remember connected versus disconnected components when you do a connected cluster theorem, like in field theory. Let's just do it for a two-site density matrix. If you have a two-site density matrix on 1 and 2, the disconnected component is just the product of the density matrices on 1 and 2. So you're throwing away the correlations between the two sites. So one way to close the BBGKY hierarchy would be to keep up through the, say, 4-site density matrices, and then the 5-site one you replace by its disconnected component, which means you know it from 1 through 4. And that closes the cycle, and then you can do this time evolution. So I'm not actually aware of any studies which have tried to just do this for super large density matrices, or up to a super high level. The intuition for why it should work is that if you know eventually you're going to a thermalizing phase, that means the correlations look like those of a thermal state. In a thermal state, you have a thermal correlation length, which means that eventually the connected components disappear at large distances, which is why the truncation should be justified. Okay, so then the question is how to implement this kind of idea, and it's not literally what we do, into a matrix product framework. And I don't want to get into the details of it. You can look in the paper, but I'll just say what the properties are of the algorithm we came up with. So it's a way for taking the density matrix you want, which is this one, after a little time step, approximating that with another density matrix with lower bond dimension, such that that approximation, unlike using the Frobenius norm, satisfies 3 properties. In our version, it's somewhat arbitrary. We exactly keep the 1, 2, and 3 site density matrices. So it's sort of like going up to level 3 in the BBGKY hierarchy. It has the other property that all the disconnected correlations between sites crossing the bond that you're truncating are kept. And then roughly speaking, if you have bond dimension left over, then it starts to fill in the rest of the connected components using the Frobenius norm. So it like does everything perfect up to 3 sites, and then just reverts to the old thing I said doesn't work very well for anything beyond that. So I don't really claim this is optimal, but I will show you what results you can get from it. So the first thing I want to compare is exactly the properties of this pure state quench. So we do a pure state quench. And what I'm going to keep track of as the time evolution goes along is trace of rho squared. Okay, so what should trace of rho squared be? Well, for the true unitary evolution, 2 things are going to be true. 1, trace of rho at any time is 1. It's normalized. But because rho is a pure state, we also have the trace of rho squared should be equal to 1. Okay? And this is proof that the state's actually pure. Now, when we do the time evolution, I'll do it two ways. One was the old way with this Frobenius norm, and then the other is this density matrix truncation, those properties. And Chris plots it in a kind of weird way. He plots the trace of rho divided by this trace of, divided by the square root of trace of rho squared. Now, the first thing you'll see is that in the old way of doing it, this ratio becomes less than 1. The only way that can actually happen is if your density matrix is becoming not positive definite, so it has negative eigenvalues. And so what happens is for a while, the ratio stays 1. That means it's pure and it's working well. And then when the truncation hits in, all of a sudden the old method completely screws up your density matrix, and it's not even a density matrix anymore. So you can get very weird expectation values. Like positive operators can end up having negative expectation values in the old method. With the DMT, the same thing happens where it stays pure for a while, and then this ratio goes up. What that's telling you is that the density matrix is saying positive definite, but rather than being pure, it's turning it into an actual mixed state. And in a way, that's kind of what we want, because we said the reason the true density matrix gets very complicated is that there's very large non-local operators which are secretly keeping track of the fact that you're in a mixed state, or sorry, in a pure state. When you throw away those complicated operators, you actually turn the state into a mixed one. So it's not necessarily bad that the entropy is going up. So that's the intuition. Eventually, the DMT starts turning the pure density matrix into a mixed one. So let's, I want to show an application of this to a pretty interesting problem that I don't think we really knew how to study before, which is Floquet dynamics, prethermal Floquet dynamics. So this is ongoing work by Norm Yao's group at Berkeley. So here's the kind of problem they look at. They have a 1D spin chain. Two of the dominant terms are static. But then you have a third term here, which is a magnetic field, which is rotating in time. So it's being periodically driven at some frequency omega. Now, at very high frequencies, defined by the ratio of the drive frequency to the interactions J, you'd expect that the time dynamics will end up being governed effectively by the average of the Hamiltonian over one period. So this is the so-called Magnus expansion. And I haven't given you the details of H, but they've chosen it such that if you average it over one period, it actually just reduces to the X term. So the question is, what we want to do is study the dynamics of a state under this Floquet evolution and see how well it's actually described by the Magnus Hamiltonian. And there's a beautiful set of work by Dima Abonin and others, which is the so-called prethermal regime. And what they prove is that up to a very large time scale, the dynamics of the state will behave like they're being governed by the average Hamiltonian. And you only see the deviation in the dynamics away from the average Hamiltonian at a time scale which is exponentially large in the ratio of omega over j. So the way they express it here is you have a parameter here, which is bandwidth over frequency. And this is the rate at which the dynamics differ from this. And that rate is suppressed as this ratio changes. So if you look at, for instance, a typical observable like magnetization, you'd expect that there'd be an exponentially long time scale where it effectively looks like it's just going to be in equilibrium under this Hamiltonian, and only over an exponentially larger scale do you see it start heating up towards infinite temperature due to the residual perturbations. So this is the idea of a prethermal phase. So the question is how would you be able to diagnose this numerically? So first they just do some benchmarking. They do a 20-site system where you could use exact diagonalization, so specifically Krylov time evolution, to get the exact solution so you can compare them. And you can see the plots here comparing this density matrix version versus exact diagonalization. So the solid line is the exact result. The dashed lines is the DMT result for different size bond dimensions of the MPO. And you see that it converges, okay, so for green and red are for two different ratios of omega over j, so it's just two different data sets. And in either case, you see the density matrix method converge pretty rapidly to the exact result. And the plot on the left is showing the energy density. It's this basic physics that, so this is a log scale here, a linear scale here, measuring the energy density with respect to the Magnus Hamiltonian. And it increases exponentially, but that exponential is exactly what's predicted by this exponentially slow heating. The plot on the right is something similar. This is just expectation value of a two-point function. You can kind of zoom in on the short time dynamics. The DMT doesn't get it very accurately. I know it kind of works, but it's a little bit of a mess. And yet, as soon as you get into the long time, then it exactly follows the exact result very closely. So I'm not really aware of another way you could actually do this. If you use the Frobenius norm, it won't work at all. It'll start repeating right away. Yeah.
How much faster is the DMT versus the exact diagonalization? Like
Well,
it's supposed to save time, right? I mean, that's
yeah, well, I mean, it depends whether I do it for 19, 20, or 21 sites. Like, the ED is doubling each time you add a site, the difficulty.
I see.
So, 20 is about the limit of what you could do with exact diagonalization. So, yeah, let me just answer it for, I'll answer your question again in a second. So it also shows this physics of turning a pure state into a mixed state. So this plot here is taking the 1D spin chain and measuring the entanglement for a cut halfway in between. So the entanglement halfway between the system as a function of time. And you can compare the dashed lines are using the density matrix method, and the solid lines is the exact method. And you'll see that at long times, it doesn't get quite the right answer. There's a constant offset, and if you measure that offset, it's log 2. Some of you might be familiar with the page correction. Page correction says if you have a pure state at infinite temperature, the entropy isn't actually what the naive volume law would be. It has log 2 in the case of a qubit less than the maximal. So a pure state has this log 2 correction. What's happening is the DMT, even though it should be simulating a pure state, the whole point is it kind of turns it into a mixed state. And so it has an entanglement which is log 2 higher because the page correction doesn't apply. Right, so for 20 sites we can compare the two, but then the DMT you can then do it for, say, 100 sites. And the cost only goes linearly in system size rather than exponential. So we don't have any reason to think it works any worse for 100 sites. So you can use this to do a lot of different non-equilibrium setups. So like this is a global quench, but you can instead consider setups where you have part of your region at one temperature, another region at another temperature, and look at quenches where you set up energy currents, so they're non-equilibrium situations. Yeah.
So if I were to use like regular PVD to simulate these systems,
yeah,
how large would I have to take the bond dimension to get the same results as DMT?
Okay, so it might depend a little bit how you do it. If you, I have a plot of that. I don't know if I'll be able to get it right away. If the method you're doing is you're taking a density matrix and then applying TBD to it, you'll find that you either have to have the bond dimension grow exponentially with time, or if you fix the bond dimension very rapidly, your expectation values won't be sensible. you'll get like negative expectation values for positive operators and so on. Except for the special case where everything is near equilibrium, then it seems to work.
Does that effect still occur for the purification method?
That's a good question. I don't know if there is a pure. Yeah, maybe we could talk about that. So when you do purification, and this is something Tridip and I have worked on, when you do purification, there's a physical side and an ancilla side. The physical side, you do regular time evolution. The ancilla side, it's kind of up to you what you do. And if you make the wrong choice for what to do on the ancilla side, then you do get exponential blowup. I think it's not clear at the moment whether there's something you can do on the ancilla side to avoid the exponential blowup.
I see.
So I don't actually think DMT is exactly the right thing to do. Maybe the philosophy is, but I don't think this is the algorithm. You can already see it's a little bit arbitrary. We said we keep it exactly through 3-site density matrix, and then beyond that, it's the Frobenius norm. And I think one result of that is if you look at convergence of properties, so this here is showing, from the DMT, we can estimate the heating rate in the prethermal regime. What is the error in the heating rate relative to Krylov as a function of the bond dimension used for the matrix product operators? And you find for low bond dimension between, say, 1 and 20, it improves very rapidly. And then beyond that, it still improves with bond dimension, but it really slows out how quickly it starts converging. I think what that physics might be is like, for low bond dimension, it's using it to correctly get the 1, 2, and 3-site density matrices. But then because beyond that, we don't really give it any direction, it now treats all operators on the same footing. It kind of reverts back to the old problem of the Frobenius norm. So perhaps that's why the convergence slows. So it'd be really cool if someone could come up with a elegant, efficient algorithm where you have a metric which, rather than sharply distinguishing between 3 and everything else and 4 and everything else, somehow smoothly interpolates and continuously weights large body versus small body things. Maybe that will give an algorithm that converges much more quickly with bond dimension. So I'd be curious if anyone has ideas about that. Yeah.
So I think I missed this. Is the Frobenius norm what the other algorithms are sort of implicitly minimizing or explicitly?
What's the difference?
Well, if you could design algorithms to minimize a particular norm, then you could start choosing different norms, right?
Yeah, exactly. So yeah, the old algorithms, it turns out everything, the center of TBD is the singular value decomposition. And if you ask what is SVD decomposition optimizing,
And
it's L squared norm, which in this context is the Frobenius norm. So what TBD is doing is saying, for a given bond dimension, how do I minimize the Frobenius distance? But really, you could use any inner product you want, for instance, in that language, and it would correspond to like a reweighted version of SVD, for instance. Okay, so for the final part of the talk, I want to talk about two-dimensional tensor networks and just give an overview of why there's tons of papers being put out all the time using the 1D methods, trying to push them to 2D, etc. Why aren't we just doing the more elegant thing and directly using an intrinsically two-dimensional ansatz? So I just want to kind of give a sketch and overview of what it is that's hard about 2D tensor networks. So first, what's the ansatz? How do I generalize the matrix product state ansatz? So now the data, rather than being rank 3 tensors, is, if we're on a square lattice, is a series of rank 5 tensors. So for each site, I have a tensor. One of the legs is associated with the qubit there, and then the other 4 legs are the so-called virtual or ancilla legs. They can have whatever bond dimension you want. The bigger the bond dimension, the larger your variational space. And then using this Penrose notation, you take all the tensors together, contract together their virtual indices, and you're left with an array of dangling indices corresponding to the wave function of the two-dimensional spin system. Okay, so the reason this kind of connectivity makes sense is the area law also applies to almost all states in 2 dimensions. The only exception we really know in 2 dimensions is if you have fermions with a Fermi surface. But otherwise, both gapless and gap states have an area law. And you can show that these PEPs can support an area law. So the entanglement structure is kind of right. But unlike 1D we can actually prove that gap phases of matter have efficient MPS representations. We certainly can't prove that in 2D. More likely, actually, there's 2D phases that might not have PEPs representations. We just don't know which. Okay, so what's difficult about working with the 2D PEPs? Well, let's consider the simplest thing you'd want to do. I have some variational wave function. You choose the tensors, you get a wave function. Suppose I just want to compute the norm of the wave function. So let's first compute the norm of the wave function in the case of a matrix product state. So I have a bra and a ket, so I have 2 copies of the MPS. Then you glue them together by summing over the physical indices, and you get some tensor network you need to contract that looks like that. Okay, so let me sort of smash it together vertically. This orange blob here, formally it has indices on the left and indices on the right, so I'm just going to represent each of those orange blobs as a matrix with indices on the left and an index on the right. And so schematically, the type of contraction you need to do is you need to sum over the legs going like this. And we can ask, well, if you put this on a computer, how long is it going to take? Well, if you look at the number of terms in the sum, each index you have to sum over chi possibilities. That's the dimension of the index, or actually chi squared in this case. And you have L indices to sum over, so it's like a nested for loop that's L deep. Each for loop runs over chi squared items. So the number of terms you actually have to evaluate is going like chi to the 2L. So in other words, naively, it looks like to compute the norm of this wave function will actually take a number of floating point options scaling exponentially in the length of the system. Okay, but actually that's a really stupid way to do this contraction. The trick is to use matrix multiplication. So what I'm going to do is first ignore all the matrices here, just focus in on these 2, and just do this particular contraction. So if you count that out, you have 1 index here and 1 index here. Each of those indexes size chi squared. So the cost of that is chi to the 4th, and then you just store that result. But once you have that result stored, you can just iterate this procedure and then iterate the procedure again. So in the end, you have to do this L times. Each time the difficulty was chi to the 4th. So really, because of the existence of matrix multiplication, the actual difficulty is linear in system size, not exponential in system size. If you do it a little more cleverly, you can show it's actually L chi cubed d. Okay, so in 1D, that's why matrix product states are usable. The norm and basically any other expectation value ends up only costing polynomial in the system size. Okay, so what would we have to do in 2D? Well, it's the same sort of thing. If I want to compute the norm, I have the bra and the ket. So I take 2 copies and contract them with each other. People use the so-called double line notation. So I have 2 copies of the tensor. This is the complex conjugated one. And I'll just use a symbol where after summing over the physical one, I get a tensor here, which is rank 8. Okay, so the full psi squared of the wave function then corresponds to this contraction of a 2-dimensional network of tensors like that. Okay, so formally, again, it's a sum. And if you ask how many terms are in this sum, well, it's basically you have to sum over chi possibilities for each of the vertical links and each of the horizontal links. There's L squared of them, so you get something like chi to the L squared, or it's exponential in volume. Now, the problem is, unlike 2D, unlike 1D, in 1D, there was an obvious order, and that obvious order defined the way I could do matrix multiplication. So it's the existence of an ordering in 1D, or causality in a sense, which let me reduce it to polynomial difficulty. In 2D, there's no analog of an ordering, and you can actually prove that to compute this exactly, there's no trick like matrix multiplication. This is actually a NP complete problem. The reason is you can actually encode like tiling problems and constraint problems like KSAT into this kind of contraction. So if you could do this contraction efficiently, there's a big class of problems you could solve. So that's why we know it's difficult. So basically, this is the curse of loops. Because there's loops, there's no causality you can define, and hence no matrix multiplication trick. Okay, so how does this translate into the ability, or the difficulty in doing TBD? Well, let me explain what the algorithm is you have to do then. So it's called the full update. So suppose we have a tensor network and I want to do time evolution. Just like in 1D, I can take the 2D time evolution and split it up into a series of two-site gates. And if I have a way to start with a PEPS, apply two-site gates, and then bring it back to PEPS form efficiently and accurately, then I'm done. Then I can do time evolution or do imaginary time evolution. So let's zoom in on the two sites I act with a gate on. I can ignore the rest of the tensors. Suppose I'm just acting with a two-site gate here. Locally, the tensor structure looks like this. I act with the two-site gates. And then you can just bring that in and get a big fat tensor here, which has higher rank. And formally, you can show, you could always replace this big fat tensor as a sum of two tensors at the price of making that bond dimension go up by a factor of d squared, where little d was the dimension of the physical index here. Okay, so you could proceed this way. It would be perfectly exact. It's just that the dimension of the tensors would go up by d squared at every evolution, and you'd be completely screwed. So we need some way, actually, to go from this big fat tensor down to a sum of two tensors without increasing the bond dimension. In other words, we need to truncate this back down to the original bond dimension. And that's the central question, how to do that efficiently. How to make a good approximation when you do that. So one of the first algorithms people came up with is you do something very naive. We have the tensor on the left. Maybe I shouldn't call it a wave function, but we have this local tensor on the left. By grouping all the indices on the left part and the right part, you can view it again as a matrix, the rows and columns, and then do the singular value decomposition. So you write theta as USB. And then these singular values, some are going to be big, some are going to be small. And then you just keep the d biggest singular values in order to reduce the rank of these matrices. And if you keep d of them, that exactly corresponds to writing that as a contraction of two tensors where the dimension here is d. And this indeed will be a decent approximation of that thing over there. So if you dress this up a little bit, this is what people call the simple update. But the problem with this is if you think really careful about this, and I learned this from Frank, and ask, what problem is the simple update exactly solving? You know, we think of it as approximating the 2D problem. Is there a problem it's exactly solving? And you can show the simple update exactly calculates time evolution on a beta lattice, which is this tree-like lattice here. So it is solving an interesting, useful problem, the beta lattice, but it's not actually solving a 2D one. The beta lattice is kind of actually an approximation for infinite dimensions. My intuition for why this is true is you can see, unlike a 2D lattice, which has loops, which are kind of the bane of these algorithms, the beta lattice actually doesn't have any loops in it, which is why...
What do you mean loops? Sorry, I don't know what you mean by loops.
Oh, a loop, I just mean that any two tensors are contracted by multiple paths, or equivalently, there exist closed loops through the network. Whereas in 1D, there's no closed loops because it's a line.
Would it help in 3D?
Well, 3D, you also have closed loops, so you're going to be in trouble. Yeah. Now you can see the beta lattice doesn't have any closed loops because it's a tree topology. It is still a cool algorithm, though. Like if you want to do a kind of mean field calculation, TBD is basically doing a mean field calculation. That's one way to think about the beta lattice. Or sorry, the simple update version of TBD. Okay, so what in principle is the right thing to do? Regardless of whether it's doable or not, let's figure out what the right thing to do is. Well, we should phrase it actually as a variational problem. So I have the state of interest on the left I got by applying the two-site gate. And I'm trying to approximate it by another PEPS, where all I'm doing is modifying the two tensors there. There's a A prime and a B prime there. Now those tensors are variational degrees of freedom. I'm trying to choose the best ones of a given size, bond dimension. And what I really should optimize, because we're just dealing with pure states here, is the overlap between the target and the variational state. You should maximize the norm squared overlap. Okay, so how do you do that? How do you choose the A prime and B prime to maximize this? Oh, and I should say in 1D, actually, if you write down how 1D matrix product state algorithm, it turns out SVD does solve this problem. It's optimal in that sense. But in 2D, SVD doesn't solve this problem. Okay, so there was a bunch of terms showing up in the thing I need to optimize. One of them is just the norm, which I was talking about earlier. So as we said, the norm is some lattice contraction that looks like this. So I have the two phases of the two sites of interest here, which is A prime and B prime. These are the ones I'm fiddling with. I'm trying to minimize it. All the other tensors stay fixed. So you can imagine I'm going to try and save some work, which is to take all the tensors besides these two and contract that network. I won't say how to do it yet, but suppose you could do that contraction. When you contract all those outside tensors together, it gives you one big tensor here, which has legs coming out here, 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 and here. So people call this, you'll hear people talk about the environment of a PEPS. It's exactly this double layer contraction. So if you ask how many legs it has 6 double legs, so it has 12 indices coming out. So it's a giant tensor, it'd be size d to the 12. Okay, but once you have that environment, the norm is just a little local contraction here. And you can now write out what the function to optimize looks like. You have the target two-site wave function theta. You have the ones you're playing with, which is the A and B. And you can write this thing out. Given E, it's some contraction that looks like this. It doesn't matter too much. But formally now, you map this to a particular pretty nasty nonlinear optimization problem. It's a quartic function with quartic constraints. So there's no like super simple algorithm, but you can iteratively try and solve it if you know the E. Okay. Okay, but then the question is, how do you get this environment? I told you that to contract, in general, contracting a tensor network exactly is NP complete. So sort of the state of the field at this moment is people proposing different ways to approximately contract all those exterior tensors to get the environment. And there's a bunch of different methods that people have proposed, but I'd say it's still a pretty active field. So the simple update actually corresponds to taking this tensor and just setting it to the identity, which is completely wrong. So one very popular method people talk about is the corner transfer matrix. This is the case where, so this is what we call a two-site environment. You contract everything but two. This is a picture for what a one-site environment would look like. And it's a particular algorithm for using something like a power method to write this environment here, which has 4 double legs, as instead you approximate it as a particular like matrix product state, like a circular matrix product state with 4 legs. And it gives you a way to iteratively try and get good approximations for the tensors here. So it's an approximate computation of the environment, but that itself introduces some new bond dimensions here, and to get it to be accurate, you have to converge that as well. It's quite complex. So when you put this all together, computing the environment and then doing this nonlinear variational update, that's what's called the full update. There's not a lot of people who have implemented this because, like, unlike Frank's 100-line Python code, this full update involves a tremendous number of rather complicated contractions. This results from what I think is sort of the state of the art right now from Philippe Corbose's group. He studied both quantum magnetism problems in 2D as well as the fermionic Hubbard model, which a lot of people have paid attention to. So this was a benchmarking paper where he's computing properties of the 2D spin 1/2 Heisenberg model. That's convenient because that's a model that Monte Carlo can basically solve exactly, so you can benchmark and say, what's the error in the variational energy or of the ground state, that kind of thing, as a function of the size of the tensors you use. So for instance, here, this is the error in the energy versus the size of the tensors you use. The simple update has the terrible property that it doesn't continue converging. That's because it's solving the Heisenberg model on the beta lattice. The full update, which is what I just talked about, it's expensive, but it does keep going down. And recently they have a slight improvement on this you can read about, which it scales basically the same way, but it's slightly more accurate at a given bond dimension. So it does work, it seems. It's just somewhat daunting to implement, so not too many groups have. This likewise is just the expectation value of the local magnetization, which is remarkably not even very good at d equals 6. I'm not actually aware, this is doing imaginary time evolution to evolve in imaginary time towards the ground state. In principle, once you have this update, it's no different to do real-time evolution. So you could look at quenches, yeah.
For the delta E, is that like normalized to anything, like the gap or something?
No, this, I think J is 1, and this is the energy per site.
Okay.
All right, the energy difference per site relative to Monte Carlo. So you can see, I mean, it's actually it's quite accurate, third, fourth digit. Though I'm not sure if you do the, like a mean field state, it would start out here at like 10 to the negative 1 or so. D equals 1, by the way, is just a mean field state, so it starts out about here.
So is it surprising that the error is so different for these two quantities? Like, 10 to the minus 4 versus 10 to the minus 2 or whatever?
This is something you could probably estimate. No, it's probably not that surprising. I don't know if I could give a...
The energy, like that delta E doesn't say anything about the overlap until you compare it to the gap, right? So
Yeah, this is telling you that the overlap in some sense isn't very good. Even though the energy difference is relatively small. I don't know if you can argue that based on the existence of the goldstones, probably. So the 2D PEPs is really a bunch of open questions. It looks pretty similar. Yeah, it depends on which gap model you pick, but well, like, I don't know, I've done something like it for transverse field icing model. It does converge faster. One interesting thing is, so in 1D, a matrix product state can only represent states with exponentially decaying correlations, gap states. In 2D, you can write down a PEPs with finite bond dimension that has algebraic correlations. So PEPs in 2, and that's related partly that gapless phases in 2D still have an area law. So it's less clear at this point whether the gap versus gapless distinction is as important in 2D as it is in 1D. The exception, as I said, is Fermi surfaces. Those have a logarithmic violation. So some questions for the audience. Yeah, one would be to just, if someone implements the full update, to just go ahead and try and use unitary time evolution. You could look at quenches of Hubbard models and so on and see how well that works. The other thing I'm struggling to think about is, unlike 1D, where like DMRG seems so canonical that there's clearly only one way to do this and it works extremely well. We've been using basically the same algorithm since 1991 or 92. The 2D algorithm, there's a lot of different choices you can make about how you do this approximation. Unlike 1D, remember 1D there was this canonical form that was clearly like the right way to fix the gauge. 2D PEPs also have a gauge redundancy, but there's not an obvious canonical form. People have proposed different ones, but if you can propose different canonical forms, maybe you shouldn't really call it canonical. So I think it's still an open question whether there's some insight to be had, like maybe there's some canonical form we don't know about where, once we implement that, this whole algorithm will be a lot simpler. And there's a more analytic question which is, as I mentioned, unlike 1D and 2D, we don't know what quantum phases of matter can even be represented as PEPs. So there's a kind of conjecture, actually, that if you have any chiral phase of matter, a gapped chiral phase like a quantum Hall state, that it doesn't even have a PEPs representation. Or more generally, I think the conjecture would go, if you have a phase of matter where the edge can't be gapped, an ungappable edge, then it doesn't have a PEPs representation. That's just a conjecture, but we need to know these sorts of things, because suppose eventually we want to give up cylinder DMRG and just do 2D PEPs. We won't really have any method to benchmark it against. And if it turns out you're using a variational ansatz that's missing phases of matter and can't represent them that you don't know, you can just get wrong answers because you're forbidding the true ground state just at the outset. So hopefully we can at least explore that. Let's see. I think that is basically what I want to discuss now. Any questions? Yeah.
For the pure state, there's if assuming like infinite translational invariant. So
Yeah.
Can it be generalized to DMT?
That's a good question. I think it probably can, but we haven't worked that out actually. We always use finite chains. That's a good question. I don't see any obstruction to it, but we only understand the finite case. I could explain like why we don't fully understand the thermodynamic limit. It's the same with TDVP actually. This TDVP method, there's a very nice way to do it on finite systems, but it's less obvious how to do it in the thermodynamic limit as far as I'm aware. How early am I? What am I scheduled to go to? I did actually have a whole other lecture prepared.
Maybe 10 questions.
Okay, let me. Where's my backpack? Can we turn this off? Okay, so I'm sort of tired of talking about numerics and even quantum mechanics. So I actually want to talk about dynamics in classical systems, non-equilibrium dynamics, and specifically the idea of a classical time crystal. So I'm definitely not going to be able to get through all the material, but I would like to at least start setting up the question of how would we even go about defining what a classical time crystal is, or what's the physics question. So this is work I've been doing with Norm Yao, Leon Balance, Chetan Nayak, and with a lot of help from David Hughes here. Okay, so rather than quantum mechanics, I want to think about much more general dynamical systems. So what's a dynamical system? Well, to start, we have something I'll call sigma, which is the state space. Okay, so this is very general. The state space, if I have Ising model, for instance, this would be the configuration of all the spins. Hamiltonian dynamics would be the Q's and P's of all the particles. Quantum mechanics, this would be the wave function. And a general dynamical system, I'm going to use a notation which is a discrete time dynamical system. Would be, we have some rule to specify what's the state of the system at time t+1 given the state of the system at time t. So in the quantum case, we'd say this is like the Floquet evolution. Okay, so that's a dynamical system. In this case here, it's deterministic. So what is a discrete time crystal? Well, we can really ask this for any dynamical system, quantum or classical. And in words, it's just, does long time behavior reflect the time translation invariance. So I have a discrete, this is discrete time translation invariance. Okay, how operationally, what do I mean by that operationally? Well, here's the way you could do it in an experiment. You prepare the system in some state, and then you start time evolving. At the beginning, it does something kind of complicated, and then it settles into some sort of steady state. And what I can do is look at that steady state and form an ensemble of measurements where I look at the state of the system at, say, every other time step. Okay, so I just start making measurements, and this is building up a probability distribution from the ensemble here. And then I can make another probability ensemble where I instead look at the odd time steps. Okay, so you wait a very long time until these build up probability distributions, and you can ask, is the probability distribution the same on the odd and even steps? And if these were different, that's an example of time translation invariance being broken. So an obvious example of such dynamics would be as follows. Let's just say my state space is a number. And I'm going to choose a rule which is that f of sigma is equal to negative sigma. So sigma t is equal to plus or minus negative 1 to t. Clearly, if I do observations on odd versus even times, you're going to see two completely different behaviors. So this is an example of time translation symmetry breaking. An example that doesn't have time translation symmetry breaking would be f of sigma equals lambda sigma for lambda less than or 1. It just goes to sigma. Goes to 0, so the long time behavior does have time translation invariance. Okay, but as condensed matter theorists, we don't actually want to think of this as a time crystal for the following reason. And that's the reason of stability. So suppose I take this dynamical rule, it's kind of like my Hamiltonian. Suppose I perturb it a little bit. So I can put here a 1 minus epsilon. Now we can see that once I put this 1 minus epsilon here, this behavior dies, and this instead actually goes to 0. So this meant that an arbitrarily small change in the update rule destroyed the time crystal. And that means the time crystal here is not actually a phase of matter. So we want a notion of rigidity. What we really want is period doubling or tripling, etc., that is robust to an arbitrarily small perturbation of the dynamics. And that then makes it a phase of matter. Okay, so that's the first refinement, is when can time translation symmetry breaking be a phase of matter? Now, it turns out for general dynamical systems, this is actually very easy to set up. Like, I don't know if you read the various press reports about time crystals. Like, one of them was physicists just found time crystals in a common item you can buy at this toy store, for instance. When they explain the time crystal, they say it's period doubling, which is robust to perturbations, like I've described here. But actually, models like that have been known for a very long time. So here's an example, which many of you are probably familiar with, is let me choose the rule f of sigma is equal to a sigma 1 minus sigma. So this is a so-called logistic map. There's a nice way to plot what the dynamics are. So if you want to know what is the state of the system at time t, it comes from iterating the function, of course, just sort of t times. And these iterated maps are well known in the study of chaos. The way to think about it is you draw the function corresponding to the map f, and then you draw the line f equals sigma here. And at long times, the behavior of the state corresponds to, I did not do a very good job drawing it. But no, I didn't make a period cycle. I chose the wrong part in the phase diagram, sorry. Something like this. So if you choose A properly and iterate the function, you'll find that no matter what sigma starts at long times it will settle into so-called, say, period 2 orbit. Now you can, okay, that's period doubling, but you can ask whether it's stable. The answer is yes. You can change A a little bit or add a linear term here or a quartic term. And it's easy to mathematically prove that the period doubling will stay. The particular value of the orbit will change slightly, but it will be period 2 up to small perturbations. And as you change A, eventually it actually goes through something like a phase transition. Well, it's just a bifurcation where it can go from period doubling to tripling, etc. But this has the property of rigid period doubling, stable to arbitrary perturbations. So it's not just rigidity, actually, that makes a time crystal interesting. So why is it so easy to get the time crystal here? It's because if you look at these dynamics, they're what we would call dissipative. So in contrast to Hamiltonian dynamics and unitary dynamics, if you look at Hamiltonian unitary dynamics, there's a notion of a volume in phase space which is preserved. So in the quantum context, that's unitarity. In the classical context, that's that you're doing canonical transformations. So it means that if you have preservation of phase space volume, it means that distinct orbits can't all converge together on a sink, right? You can't have contractive dynamics. The dynamics of this system here are strongly contractive. No matter where you start, all those orbitals, all those different orbits, eventually just converge down onto the same one. It's like dissipation, it's like friction in this system. So if you have a system with friction, so to speak, it's very easy to get period doubling. So the really special thing about time crystals, like is when can you get stable period doubling in the absence of dissipation? Now I am done, right? So, okay. Well, I think this is an interesting problem, actually, that gets into very wild non-equilibrium classical dynamics about trying to figure out when either classical closed systems or classical systems in the presence of a bath are able to realize time crystals. And we think actually that if you have classical systems in the presence of a finite temperature bath, which provides both dissipation but also noise, that you can actually realize period doubling classical systems as well. So that's this work with Norm, if you're interested. So I'll awkwardly stop at that point there.
All right, well, that wraps up the summer school. Thanks everyone for attending. There's a survey that we'd like you all to fill out, and we hope you will come next year.